Welcome to Quantum Curious. And in today's video, I'm going to discuss a very important concept, that is the concept of the partial trace. So usually we are given with the state of a system describing uh, a very large system, and it is usually composed of subsystems. So we are usually interested in the state describing the subsystem. So how can we do this? So the answer is the partial trace, and this is the formalism that is usually used in obtaining the state describing the subsystem from the state describing the whole system, that is the large system. So consider an example that we have a setup and we have two players in it, that is Alice and Bob, in usual experiment or thought experiment of quantum information or quantum cryptography. So there is a state that is row AB and describing the state of the whole system that is composed of Alice and Bob. So but Alice and Bob are only interested in their individual systems. So how can we describe the reduced state of these two subsystems that is describing the system of Alice and Bob? So it is usually done by using the concept of the partial trace. So let's jump into it, and we start with a motivation. So our question is that how can we compute the reduced states from of us a larger system? So first start with an example. So we have a joint state, that is state row AB, and it is composed of the tensor product of two states, that is describing the individual states of two subsystems. So state A is a 0, 0 state and state B is a 1, 1 state. So we want to know what are the reduced states of these joint state. So it is easily seen in that case is that row A is the reduced state of the system of the subsystem A, and it is uh, described by a 0, 0, and state B is in state 1, and it is described by the cat 1 and Brown or their outer product. So in this example, we can see that we can easily find the state of the subsystem by just looking at it, because this joint state is in the form of the separable state. But as we will move on in the later slides of this video or lecture, we will see that as the joint state will get complex, the method or the mechanism to obtain the reduced states will get more complex, and it could be simplified by using the concept of the partial trace. So let's see another example. So we have process uh, uh, that is preparing two states. So either it is preparing that state or that state. So uh, so the probability of obtaining these two states is equal. So we can write the joint state by the addition of these two states, and where half is describing their individual probability. So in this case, we can see that by just mere looking at this, it is not easy to obtain the individual states of the subsystems. But uh, but scrutinizing a little deeper, we can see that we can obtain the individual state of the subsystem A. So row A could be written as, we can see that it is composed of 0, 0 and 1, 1 state. So we can write it easily, that is the state row A of the subsystem A could be written in that form. So it is easier, but it is a bit harder from the previous example, because here uh, the joint state has a bit complex form. So generalizing this procedure, we can introduce the concept of the partial trace. So we have again the state row AB that is prepared by the by a process that is generating these two states randomly, and we want to know the reduced state of this of the system A or the subsystem A. So it could be solved, or it could be obtained by tracing by taking trace over B, and you could see that if we take the trace over state B, it could be easily simplified because using the cyclic property of the trace, we can convert this trace into an inner product. So the inner product of 0, 0 is 1, and inner product of state 1, 1 is also 1. So simplifying these traces, we could see that we can obtain easily the reduced state of system A, that is the row A, and it is again in the form that is given previously. But it is much easier and much appealing to see that how can we obtain the reduced state from the joint state. So again, it is a much harder problem, and the state, that is the joint state, has a much complex form. So we have state row AB, that is the Bell state, and it is a maximally entangled state. So initially we cannot see that how to obtain the reduced state of system A and system B. But taking trace over B or ignoring system B, we can easily calculate the reduced state of the subsystem A. So taking trace over B, we can simplify uh, the whole process. So by seeing there that taking trace over that quantity, it is going to be 1. Taking trace over that quantity, it's going to be 0, because 0 and 1 bit are orthogonal to each other. And in that case, the inner product of 1 and 0 is also 0, and inner product of 1 1 is going to be 1. So the reduced state in that case is again a maximally mixed state as we obtained previously. But in this case, the original, that is the joint state, has much more complex form than the previously we have seen. So in that case, just mere seeing this joint state, we cannot guess what is going to be the reduced state of the subsystem A. So that was you can say, the more mathematical way to seeing the partial trace. So now I'm going to discuss a more uh, general formalism of calculating the partial trace. That is more mathematical, and later we will see that uh, how can we realize it much more in physical scenario. So again, we have row AB, that is a general reduced state, and it is decomposed into its orthonormal vectors, that is describing the subsystem A and subsystem B, and taking trace B over this joint state, we can easily obtain the reduced state of subsystem A. So taking trace B, we could see that it is just boils down to the inner product of the state L and state K. So in order to be the inner product to be 1, they both have to be the same form. So you could see that uh, if we assume that L and K are equal to each other, we can obtain the reduced state. As you can see that the indices has also changed. So this is the more mathematical way to see the operation of the partial trace. So now I am going to review, that is, there is an alternative way to see the operation of partial trace, and that is more physically realizable. So consider we have state row AB and we perform a measurement on system B. So performing measurement on B uh, in projective measurement will collapse the system B, and we will have remaining the system row A. So in this way, the system reduced system A does not depend upon the measurement of system B. So this could be obtained by a POVM, that is describing as the tensor product of identity over A the the projective operator on system P, and here cat P is the basis of the or you can say the orthonormal basis vectors on the subsystem P. So the probability of getting system B or outcome B could be described by this quantity, and the post measurement state could be described as this, as we have seen in the previous lecture uh, how to obtain the post measurement state with the help of the cross operators. So again, we have this post measurement state, and we want to know the reduced state that uh, of that post measurement state. So we will again will trace out the subsystem B, and again taking the trace over the state B and plugging in the general form of the row AB that we have described earlier, we could obtain that kind of form, and it could be easily obtained. There is not that much of complexity here. So you could see that we have to solve this trace over B. So it could be solved as you can see that if K and L are going to equal to B, then it is going to 1. And again, using the partial or cyclic property of the trace, we could make it the inner product of uh, the two similar orthonormal or identical orthonormal vectors. So we are going to have this kind of state. So we know that the state row A, that is the reduced system of subsystem A, will have this form because it depends upon the uh, it depends upon the probability of having this reduced state row A, and the probability is PB. So again, putting that form that we have obtained from the previous expression in this form, we are going to have this quantity. So again, we could see that this is the state row A we desired to obtain. So again, we could see that in order to obtain the reduced state in an alternative way, we have to implement trace B or the expression of the post measurement state, and again we are going to have this form if we plug in the general form of the joint state row AB. So in this case, we are going not to uh, use the cyclic property of trace, and we will obtain that form. So we did use the cyclic property of the trace in that case, and we obtained that form of expression. So by looking over it, we could see that this state is again the general form of the state row AB. And we could see that the state reduced state row A on the measurement B could be obtained by projecting the projecting the system B from both sides by the state B, or measuring the system B in the basis B, and we could easily obtain the trace that is the reduced state of system A. So in summary, we could calculate the reduced state of subsystem A by carrying out the measurement on subsystem B with the help of the basis vector. So this was it for today, and we have seen that the concept of the partial trace and how can we use it to obtain the reduced state from any kind of joint state. So we saw both the aspect of the partial trace, that is the more mathematical way of seeing it, and more physical way of seeing it by seeing it as a measurement on the subsystem. So this is for today, and in next lecture we will see a more concept related to quantum cryptography and quantum information theory.